Okay, so let's go ahead and take a look at this objective. So this objective, we're going to first start out with the difference between something being convergent and something being divergent. So something is convergent if it tends towards one point or they approach each other. And something being divergent, like a series or a sequence, means that it goes towards infinity or it doesn't exist. Okay, so we're first going to go back to integrals with this first objective, and we're going to look at what it means for an integral to be improper, and then how to evaluate those integrals. So an integral is improper if there's a discontinuity in the integral. So between a and b, there's some sort of discontinuity. So that's this first thing here. Or if one of the limits of integration is negative infinity or positive infinity, or you could be going from negative infinity to positive infinity. And what you're going to try to do is try to evaluate that integral. And if that integral cannot be evaluated, then we call that integral divergent. Okay. If we can evaluate that improper integral, then we say that that improper integral is convergent, and it converges to that evaluation number. So let's go ahead and take a look at this first example. So this first example here, what you notice is that one of the limits of integration is infinity. So what we're going to do is, it's in the b placeholder, so we're going to take the b value, and what we're going to do to evaluate the improper integral is we're going to take the limit. So we're going to take the limit as b approaches infinity, and it's infinity because it's infinity on the top here. And we're going to say that I'm going from 0 to b of dx over x squared plus 1. And now what you're going to do is you're just going to evaluate this antiderivative as if you had a value for b. Well, we know that any antiderivative that has no x in the top other than dx and just an x squared plus 1 on the bottom is arctangent. So this is not a u substitution, this is arctan. So the limit as b approaches infinity, limit, we're taking the antiderivative of dx over x squared plus 1, which is arctan of x, and we're evaluating this from 0 to b. And now what we're going to do is we're going to take b and we're going to plug it in for x, and we're going to take 0, we're going to plug it in for x. So we take the limit as b approaches infinity, arctangent of b minus the arctangent of 0. And now you're going to ask yourself, well, how do I evaluate the arctangent of 0? You have to remember something from a previous class. You have to remember how to evaluate tangent inverse. So the tangent inverse, or arctangent, is valid either in quadrant 1 or quadrant 4. And so what we're doing is we're going to say tangent of what angle is equal to 0? Well, the tangent of 0 is equal to 0. So arctangent of 0 is 0. So what we're actually doing when we do arctangent is we're finding this 0 here represents the angle measurement. So we're taking the limit as b approaches infinity, arctangent of b minus 0. Now you have to know, in order to be able to evaluate this limit, you have to know what arctangent looks like. And arctangent is basically tangent turns sideways. And so you actually have horizontal asymptotes at positive and negative pi over 2. So as b gets larger and larger, so more positive values, what you're going to get is the arctangent of b is going to be pi over 2. And then you're going to minus 0. So then overall, you get pi over 2, which means that this original antiderivative is equal to pi over 2. We say that this integral is convergent because it goes to a number and it's not going to negative infinity or positive infinity, or it cannot be evaluated. Okay, so now we're going to take a look at another example here. Again, determine whether or not this is convergent or divergent and what it converges to, if it converges to something. So again, the limit is at infinity. This is in the b spot, so we're going to take the limit as b approaches infinity, antiderivative from 1 to b of dx over x, which is the same thing as the limit as b approaches infinity of ln of x, and we're evaluating this from 1 to b. So this is the limit as b approaches infinity, ln of b minus the ln of 1. Ln of 1 we know to be 0, so this is the limit as b approaches infinity of the ln of b. And again, you would have to know kind of what this graph looks like. And so this is going, this ln of b, as b gets larger and larger, this is going towards infinity. So this actually diverges. And this improper integral is equal to or goes towards infinity. Okay. So now what happens when it's something different and it's not, you know, my a and my b value are not actual either negative infinity or positive infinity? We actually have a discontinuity. Where is my discontinuity? My discontinuity is whatever value of x makes the denominator equal to 0. So in order to do this, we're going to split this integral. We're going to go from 0 to 1 and then from 1 to 2 to evaluate this whole antiderivative. Now, when we take our limits, we're taking our limit as a, and I'm going to use a, I could use b, but I'm going to let my improper spot be equal to a variable. If I want it to be consistent, we could change these to b's if it would make you feel better. And I'm going from the left side. Notice you're going from the left side of 1 because I'm going from 0 to 1. So on this side here is the left side of 1, and because I'm going from 1 to 2, this is the right side of 1. So remember with limits that we can approach it from the left and from the right. And then what I'm going to do is I'm going to simplify this. Remember that my cubic equation, I can factor my cubic. So then when I reduce, I get x squared plus x plus 1. So now, again, I already changed all these a's to b's, so let's go ahead and do those. So I took my here, separated off my original antiderivative into two separate ones. I split it across the discontinuity. So I take it from the left, and then I take it from the right. And then I reduce using my factoring of cubes. I take my antiderivative, and my antiderivative is just normal because antiderivative of x squared is 1/3 x cubed, antiderivative of x is 1/2 x squared, so on and so forth. And then when I go and I evaluate my limit, because there's no places where I can get 0 in the denominator when I plug in 1 in for my b's, I can go ahead and just plug in all of my 1's in, and then I evaluate, and I get 20/3, which means that my original antiderivative way up here is equal to 20/3, and we would say that it converges to that value. Okay? So now, again, doing the same exact thing, but now I'm going from negative infinity to positive infinity. So I'm going to pick my favorite number. I'm going to pick 0 because it's easier. And I'm going to split my antiderivative. Make sure you change this. It's important here. I made a typo. It should be a 0, not a 1. You need to split your antiderivative across the same value. I'm going from a, because that is my lower limit, to negative infinity, and then my upper limit is my b, which is positive infinity. Again, this antiderivative of dx over 1 plus x squared is arctangent. I go ahead and I evaluate my arctangent, And when I evaluate my arctangent, I get a positive pi over 2 plus a pi over 2, so I get pi. Okay? And that is it for this objective.